Welcome to the fifth video in the FOQUS Basics series, and in this video we're going to show you how their streams work when we have an iterative simulation in our FOQUS Flowsheet. So for this example we're going to start with a new FOQUS file. So we're going to call this file their stream example, and we're going to save this file in our desktop. So we're going to click Ctrl S, and when this message box appears we're going to click continue. So we select our desktop and save the file. And now we go to our flow sheet and we create a node. We're going to call this first node mixer, and we're going to create another node and we're going to call this node splitter. So once we created the two nodes, we're going to click this select button again, and now we're going to open our node editor and we're going to go to our mixer node. So for our mixer node, our input variables is the feed and the recycle, and the default value for the feed will be 2 and the default value for the recycle will be 1, and we're going to set the minimum maximum values from 0 to 10. And our output variable is called outlet. And the equation we're going to use to relate these inputs to our output, we're going to type it in our node script. So we're going to start with the output equal to our inputs. So our output is called outlet, and our inputs is called the feed and the recycle. Okay, so first we're going to click this button, so to set the values of our feed and recycle as the default values. And to make sure that we typed in everything correctly, we're going to click this green run button to test only the mixer node, and the simulation is successful. And our output variable, or the outlet, is indeed equal to 3, which is 2 plus 1. So great. So next thing we're going to do is go to our splitter node and insert our input variable. Namely, we're going to call it inlet. And we're going to set the default value equal to 3, and our minimum maximum value goes from 0 to 10. And once again, we're going to click this default button. And we're going to select yes, and our inlet value then becomes equal to the default value of 3. Now for our output variable, we have two outputs this time. We're going to call it outlet and recycle. And to relate the node outputs to our one input, we're going to once again do this f equals x and f equals x. So our first output is called outlet, and our second output is called recycle, and these are related to our inlet. And I'm going to set the outlet to be equal to 0.75 times our inlet, and we're going to set our recycle node equal to 0.25 times our inlet. So we're going to save the file by clicking Ctrl S and clicking continue. And once again, we're going to run this node, only the splitter node, to test to make sure that it works, and it does work. So input variable is equal to 3, and outputs, the output is equal to 2.25 and 0.75, which is what we would expect. Now, the next thing we're going to do is we're going to connect these two nodes using an edge. So I'm going to click this Add Edge button, select the mixer, and then click the splitter. And I'm going to click this Select button again. And I'm going to go to our edge editor. I'm going to select this edge, and I'm going to click this box to make our edge editor bigger. Then we're going to unclick this box for lock editing, and we're going to add a variable. So we want the outlet of the mixer equal to the inlet of our splitter, which is what we want. That's great. So we're going to again click this box so that we don't accidentally change these values. And before I forget, we're going to click this edit again and adjust the curvature, and which will be useful because we're going to add another edge that goes from splitter to mixer. So after adjusting the curve, we'll just click the edge and we see that the curve has changed. Now we're going to add another edge by clicking this add edge button, and we're going to select the splitter, and then it's going to go from splitter to mixer. So once again, I'm going to select the select button, and I'm going to click this edge so it goes from the splitter to our mixer. I'm going to uncheck this box, and in this case, because we want the recycle variable of the mixer equal to the recycle variable of the splitter, we can actually click the auto button. And as you can see, the recycle for the splitter equals the recycle of the mixer, which is what we want. So we're gonna again click this log editing to make sure that we don't accidentally change these values, and we're going to close our edge editor. So what we're going to do next is click this button right here to determine the tear streams. And as you can see, this arrow got changed from a dark blue to a lighter blue. So what a tear stream does is it will determine which node to run first, and in this case, the splitter node is actually going to be run first whenever we click this green button to run the entire flow sheet. And this tear stream also determines if we have convergence in the solution generated by this flow sheet. And if we open up the node editor, and we go to our mixer stream, so our input variable, as you can see, the recycle is highlighted in pink to indicate that this variable right here is connected to another variable in the splitter node via this edge. And if we click the splitter node, as you can see, the inlet variable is highlighted in yellow to indicate that not only is the inlet variable connected to a variable in the mixer node via this edge, but this variable is also a tear stream variable that will be used to determine whether or not we have convergence in our flow sheet and our solution. So we're going to open our settings, and for the tear solver, so the solver that's going to be used to determine what value of the inlet and outlet variable should be for the splitter and mixer respectively, we are going to use a solver, and we have two options. So we have the WhiteStein and the direct solver option. So the WhiteStein approach was actually developed in 1958 by WhiteStein, and this work has been published in the communications of the ACM. Okay, so our goal is to have our input variable x, which is inlet of the splitter, be equal to the output variable g of x, which is outlet coming from mixer. So that's our objective in this case. And what the direct substitution does is, for our next iteration, the value of inlet will be set exactly equal to the value of the outlet. For the WhiteStein approach, on the other hand, we first need to compute the slope m, which is equal to the value of the outlet at the current iteration minus the value of the outlet from the previous iteration divided by the value of the inlet from the current iteration minus the value of the inlet from a previous iteration. And then we compute this acceleration parameter theta, which is a function of our slope m, and then the value of our inlet at the next iteration is a function of our acceleration parameter theta, as well as the values of the inlet and outlet from our current iteration. So going back to our FOQUS flow sheet, so we have our two options. So in this case, we're going to select direct. I'm going to leave the tolerance value as is, and however, we're going to click this to determine whether or not we have convergence. So the difference between absolute and fraction of range, you can think of it as absolute and relative error. So going back to our PowerPoint slide, how FOQUS determines whether or not we have convergence is it will calculate the error, and we have two types of error, the absolute error or the relative error. So the absolute error is equal to the new value minus the old value of x and g of x that we have. So in this case, the new value of our outlet minus the old value of our outlet. and the other error is new value of our inlet minus the old value of our inlet. While for the relative error, on the other hand, it uses the new value of our TerStream variable minus our old value of the TerStream variable divided by the variable range. So in this case, the relative error would be the new value of outlet minus the old value of outlet divided by the range, and the new value of our inlet minus the old value of our inlet divided by the range. In this case, our range is 10. So going back to our FOQUS flowsheet now. So we select the fraction of range, so we want to use the relative error. We set the iteration limit at a default of 40, which is fine. And in this case, we do want a log to be created. And what the log does is it will record what the values of the TerStream variables are at each iteration, which can be very useful when we try to analyze the results to make sure that we actually do have convergence. And we're going to select this box to enforce the bounds. And the last item here is in the case that we use the WhiteStein solver option, and in this case we can set the minimum and maximum value of our acceleration parameter theta that is shown on the PowerPoint slide. But in this case we don't have to worry about the WhiteStein option because we are using the direct solver. So we're going to click OK, and we're going to save this file by clicking Ctrl S and clicking continue, and then we're going to run this flow sheet. And as you can see, the run is successful, and we're going to check several things now. So for our mixer, we have our input variable feed and recycle equal to 2 and 0.6679, and output variable is indeed equal to 2.6679, which is our feed plus recycle. Now if we check the splitter node, our inlet is equal to 2.671, which is slightly different from our output variable outlet here. So 2.6679 versus 2.671. So there's a slight difference, and again, that's because of the tolerance value that we set. If we would like to make the value of our inlet and outlet closer to each other, we can do that by adjusting the value of our tolerance. So instead of using 0.001, we could add another 0 here and use 0.0001 and click OK, and simply rerun the flow sheet. So once again we have a successful run. So I'm going to go to the mixer node, click the output variable, and in this case our outlet is equal to 2.66699 and our inlet is equal to 2.6679. So we're getting closer, and for one last time we're going to go to our FOQUS flowsheet settings, and now this time add another 0 and in our tolerance and click OK, and we run the flow sheet. So once again the run is successful, and we go to our mixer node. Output variable is equal to 2.66668 and output variable is equal to 2.6667. So we keep getting closer and closer, and how close you would like it to be? Well, again, it depends on you. So the best option we have for making sure that the answer is as close as possible is, again, by experimenting with the tolerance, which is what we just did. So I'm going to close this. Okay, so now we're going to go to our ter log. So as I mentioned, when we open the settings here, we opted to have FOQUS automatically generate the ter log, which shows the values of the TerStream variables at each iteration. And to access a ter log, all the user needs to do is go to your FOQUS working directory, and in this case we already have the folder open, so we're going to access that, and we're going to open our latest file, terlog3 in this case, because we ran the flow sheet 3 times, but terlog3 is the one where we used our strictest tolerance. So we're going to open this Excel file, and we're going to select these and make the cell wider. So the information that is contained in this file is our TerStream variable, namely our inlet. For the splitter node, and this variable is highlighted in yellow, as I mentioned, to indicate that this is a TerStream variable that is used to determine whether or not we have convergence. So this is why the inlet variable from splitter is shown on this Excel file. And we have the minimum maximum values, which is going from 0 to 10. And the x values shown on this Excel spreadsheet shows the value of our inlet variable at each iteration. So at the initial guess, we have inlet equal to 2.66699, and at our first iteration, we have inlet equal to 2.6667, and after the first iteration, FOQUS determines that it is done because our error value is smaller than our tolerance value. The other variable shown on this spreadsheet is g of x, which is the value of outlet at our iteration. So from our initial guesses, the value of the outlet variable for the mixer stream is equal to 2.66674, and at the first iteration, the value of the outlet variable from the mixer node is equal to 2.66668. And once again, FOQUS finishes the run after the first iteration. And these two items show the value, what the value of x is for the next iteration, suggested by our solver. In this case, we use the direct solver. So the direct solver recommends that the value of x for the next iteration be equal to whatever g of x is at the current iteration. And finally, the last item I would like to show is the error value. So going back to our FOQUS flow sheet, we open the settings. Our tolerance value is equal to 1e negative 5, or 1 times 10 to the power of negative 5. And as you can see, our first error is equal to negative 2.4 times 10 to the power of negative 5. And because the absolute value of the error is bigger than our tolerance, we don't have a satisfactory answer, so which is why we are doing this iteration. And after our first iteration, our error value is equal to negative 6.1 times 10 to the power of negative 6, and the absolute value of this error is actually smaller than our tolerance, and this is why FOQUS decides to stop the run. So this concludes our tutorial regarding how to set up a flow sheet in the case that we have an iterative flow sheet and how their streams work. So thank you for watching.